All right, so depending on our domain, the graph of an exponential function can appear to be linear. Now, the graph here is really not linear. And so that's what I want to kind of talk about here is because the slope is determined by the first 2 points or the next 2 points or the next 2 points. And if we look at these, we can find out that if we're between 0 and 1, the slope is going to be 59. But between 0 and the second one over here, that slope is 61. And so each one of those is going to be a different slope. And really, if we had a, like I said, a different scale, what we would end up seeing is it would look something more like that. Well, it wouldn't have that, but it'd be more like that. So it's going to have more of a curvature than what you see here. But because of our scaling, it's going to look a little bit different. So what we want to do is to see if we can actually draw a graph and make it look halfway decent. And it's not going to look very well because we're going to have too many decimal places. So 5,000 is invested at a Union Saving Bank for your CD that earns 5.61% compounded continuously. Graph the amount in the account as a function of time for a period of 4 years. All right. So X and our future value. And we want to start at time 0 and then go to 1, 2, 3, 4. And again, we're going to do A equals P E to the RT. And this time we're investing 5,000. E to the rate is going to be 0.056161 times our t. And I'm just going to place t as my x. And so those are going to be my x values. And I used x because I have to graph this on a plot here. So we'll have 0, 1, 2, 3, 4, 5. And again, they're not even spaced out very good there. All right, so let's go calculate those and then we'll come back. All right, so let's clear that. So we're going to have 5,000 times e to the r 0.0561 times 0. So that's going to be 5,000, which you expect because e to the 0 is just 1. 1 times 5,000 is that. But we needed a baseline, so we started with that. And now we're just going to change that 0 to a 1, and we get that. Now we're going to change it to a 2. And we get that. We'll change it to a 3. We get that. And we'll change it one last time and to a 4, and we get that. All right, so let me write all those down. And so basically, we're going to go just to, I mean, technically, we probably aren't even going to be able to do the tens or hundreds even, but we'll get close here. So we'll write it down as what they're supposed to be, and then from there, what we end up looking like graphing wise, that's going to be another thing. So here we said that was going to be 5,000. That was 5,288.52, and this was 5,593.68. This is 5,916.46, and this is 6,257.86. And again, we're going out to the two decimal places because this is to the nearest penny, and that's what we're going to be looking at. But now, what can I graph on the chart? Well, we're not going to be able to graph that well. So we have 1,000, 2,000, 3,000, 4,000, 5,000, 6,000. All right, so at 0, so again, 1, 2, 3, 4, 5, 6. 0, we're at 5. So that's about the only dot that I'm for sure of. The rest of these are just kind of guesses. These are 1, 2, 3, 4, 5, and this is going to be years, and this is going to be dollars, and it's going to be well, we won't. Yeah, these are thousands because I didn't make it 1,000 here. All right, so thousands of dollars. So 5,000, then we'll have 5,288. Well, that's going to be, somewhere around there. Two is 5,593, so it's going to be about halfway. So maybe about there. Three is going to be almost 6,000. So somewhere about there. And four is going to be over 6,000. So maybe about here. Okay. And at least it looks a little bit like a curvature here. And so it's going to be kind of going up like that. Okay. And again, if we did this in Excel, you could actually see it a little bit better and you could see the curvature. It would plot it with actually to the nearest penny and we'd be good to go. All right, so let's stop there and we'll come back for some more.